define antenna and define some of the parameters of the antenna. So there are various definitions of antenna. You can take any of these definitions. The first definition is a standard definition by the IEEE. The IEEE stands for Institution for Electrical and Electronics Engineers. This is a world body or a global body which determines the standards, electrical standards of all devices, all systems that you are seeing. Your mobile phone that you are using is standardized according to IEEE. 5G, 4G, all these are standardized according to IEEE. So the IEEE standards are accepted globally. So this is a professional body. The definition due to this professional body IEEE is on the part of a transmitting or receiving system that is designed to radiate or to receive electromagnetic waves. This is the definition by IEEE. You can be a part of IEEE by being a student member of the IEEE. That has many advantages, particularly networking. You will learn or you will know many people worldwide, internationally. You will know many people in the IEEE. It is related to electrical and electronics engineers, computer engineers. Everybody is, most of the people are member of IEEE, so you can be a member of IEEE. Then there is a book by Sullivan and Thiel. In that book, the definition is, it is appropriate to view an antenna as a transducer that converts a guided or bound wave. Guided is propagating, bound means it is not guided, it is not propagating, it is stable or stabilized wave. So guided or bound wave on a transmission line to a free space electromagnetic wave for a transmitting case, or vice versa for a receiving case. Vice versa means the opposite. So it will be in the opposite case, it will be converting an electromagnetic free space electromagnetic wave to a guided or bound wave on a transmission line, that is for the receiving case. It is the definition by Sullivan and Thiel. The book by Sullivan and Thiel gives this definition. I usually discard this definition. Usually I do not use this definition. This is a very long definition and it is not very useful definition. This can be put in a very concise form, that is put by C.A. Balanis, Constantine Balanis. In his book, this definition is given as the transitional structure between free space and a guided device. This is the most concise definition for an antenna. It is a transitional structure between free space and a guided device. That is the definition by C.A. Balanis. This book you will be using if you take the course on antenna in your third semester. I think in the third semester there will be a course on antenna. If you take that course, you will be following this book, C.A. Balanis. Then in the dictionary, if you look at the dictionary, the Merriam-Webster dictionary, that gives it a definition: a usually metallic device such as a rod or a wire for radiating and receiving radio waves. This definition is also not appropriate because all antennas are not metallic devices. There are dielectric structures which also radiate, particularly the dielectric resonating antennas. They radiate. Therefore, it is not proper to say metallic device. So this definition also I do not use. I use the definition by IEEE or by C.A. Balanis. These two definitions, if you use in your answer script, then the examiner will accept them without any reservations. Now, what are the functions of the antenna? From the definition, you can see what are the functions of the antenna. Let us list the function of the antenna. The first function is it converts guided wave to external propagating wave and vice versa, which means either it converts a guided wave to external propagating wave. What is meant by guided wave? Wave which is guided by a guiding structure. Guiding structure is like a waveguide or like a transmission line. Both of them are guiding structure. By the guiding structure, we mean the wave is designed, channel. A channel is designed and the wave is channeled through that structure, through that channel. So that channel is the guiding structure. That channel can be a transmission line. That channel can be a waveguide. I hope you have studied this in your waveguide. It is a channel for electromagnetic wave. So conversion between guided wave and external propagating wave, and vice versa. Conversion of external propagating wave to guided wave. So when you say conversion, it will be both guided to external, external to guided. Then on the second function is radiation pattern shaping. What does that mean? The radiation will occur in a particular pattern in the free space. It will not go everywhere. When you design the antenna, the radiation will not be in all possible directions. There may be, if you may be interested in radiating the energy or radiating the power in a particular direction. So the pattern is to be set to that direction, so to a particular region. So the radiation pattern is to be set so that the radiation is in a particular region. The radiation occurs in a particular region or space. Then control of the polarization control of the polarization of the electromagnetic field that is being radiated. So you should have control over the polarization, which means if you want to radiate linear polarization, radiate linear polarization. You want to radiate circular polarization, radiate circular polarization. Depending on the particular need, you can design an antenna to radiate linear polarization or circular polarization. Then to be in synchronization with other antennas, which means if you are radiating an antenna, if one antenna is radiating, other antenna is receiving, then both of them should be in synchronization with each other for radiation to be properly received. So synchronization with other antenna. So these are the four important functions of one antenna. So if you have an antenna, these are the four important functions. Then let us come back to some mathematical preliminaries that you should have studied in your school days and college days. So these are on angles, and angle is a two-dimensional thing, two-dimensional entity, and solid angles, which is its equivalent in three dimensions. So angle and solid angle. Now look at this figure. In this figure, you are seeing a circle of radius r, and if you have a circle of radius r, then an angle of 1 radian is defined as on the angle subtended by an arc on the perimeter of this circle, whose length is equal to r, which length is equal to its radius. So arc length is equal to the radius of the circle. So that arc length, the angle subtended by this arc length at the center of the circle, gives us 1 radian. So 1 radian, angle 1 radian is defined by this. Then how many arcs are there? total angle is 2 pi. Therefore, the perimeter length of the perimeter will be 2 pi r. Based on that, we have defined what is the perimeter. The perimeter of a circle is 2 pi r, because for each r, the angle subtended is 1 radian. Therefore, the total perimeter will subtend a total angle of 2 pi r. Similar thing, instead of a circle, you consider a sphere. Now length becomes area. So an area, A is equal to r square. R is the radius of the sphere. If A is equal to r square, so the area whose value is r square, r being the radius of the sphere, so the angle subtended by this area will be a solid angle. So the angle subtended by this area at the center of the sphere is called 1 steradian, which is a solid angle. Its unit is steradian. Radian is the unit of angle. Steradian is the unit of a solid angle. So it is 1 steradian. So that we can see in this manner the area. If you are considering area, considering a spherical coordinate system, area is equal to length into width. So consider an infinitesimally small area. So if we consider an infinitesimally small area, the length along the theta direction will be d theta, length along the phi direction will be sin theta d theta. Therefore, d omega will be equal to sin theta d theta d omega d phi. So therefore, d omega is the solid angle subtended by an infinitesimally small area at the center of a sphere or at the center of a spherical coordinate system. So that is the d omega is the elemental solid angle. So elemental solid angle d omega is equal to sin theta d phi. If you want to find out the solid angle due to the complete sphere, it will be integration of d omega over theta and phi. So if you integrate it, it will give you 4 pi. So omega will be 4 pi for a sphere. And now we'll come to different types of antenna. We'll start with the basic antenna, which is called an isotropic radiator. Isotropic means it is same everywhere, in every direction. It is same. It is independent upon direction. So it is isotropic. So if you have a antenna or a point source, usually this is a point source, and as you know, geometrically the point exists in the definition, but physically the point does not exist. Therefore, isotropic radiators are radiators by definition, but they are not physical radiators. Physical radiators, we can design physical radiators which try to mimic the isotropic radiator, but they will not meet the criteria of isotropic radiator ideal. So this is an ideal radiator. This radiator radiates equally well in all directions. So from the center, if you put this radiator at the center of a sphere, on the surface of the sphere, everywhere you will get the same amount of radiation. That is what is isotropic radiator. So if you put an isotropic radiator at the center of a sphere, on the surface of the sphere, everywhere on the surface of the sphere, we get same amount of radiation. It is fictitious because it is a point source. In the isotropic radiator is a point source. Point does not exist physically, therefore it is fictitious. Now the power density due to the isotropic radiator is equal to W0. W0 is the power density. If we say W0 to be power density, as you know, how do you define density? Density is whatever you are considering. Here we are considering power, so it is P radiation and its distribution over the surface. Surface is 4 pi r square. So W0 is equal to P radiation divided by 4 pi r square. So that gives us the power density of an isotropic radiator. It will be, unit will be watts per meter square. Remember this W0, it is very simple, total power by total area. So P radiated power by total area on the sphere, surface of the sphere is 4 pi r square. And unit is watts, power unit is watt, and 4 pi r square unit is meter square. So W by meter square. Then the radiation intensity, what is the, how intense is the radiation in any direction. So this is power densities for over all directions. Now the radiation intensity is power density into r square. So that is P rad by 4 pi. So that is equal to W by steradian. So that also you can define in this manner. Intensity, radiation intensity is equal to total power radiated by the solid angle subtended by the radiated area. So whatever area is illuminated by radiation, that area, the solid angle subtended by that area, the ratio of that power by the solid angle subtended by that area gives us the intensity. Now let us come to the field regions. So once the electromagnetic field is radiated from a source, then whether the field will be same everywhere, or at this near the source, far away from the source, in the intermediate regions between the source and the far away points, whether the fields are same or different. So that let us consider. So we'll start with a small antenna, which means the size of the antenna is very small compared to the wavelength radiated by the antenna. If lambda is the wavelength radiated by the antenna, and A is the radius of a sphere which encloses the antenna completely, and which is the smallest sphere. Smallest sphere enclosing the antenna completely has a radius A, such that A is very small compared to lambda. Under that condition, we can define the radiating fields in this manner. You can see the deep blue portion, that is the sphere which is enclosing the antenna. Around that there is a light blue region. Around that there is a pink region. The light blue region is called the reactive near field. In this field, this is called, why it is called reactive near field? Region is in this region. First is it is near field because it is near to the antenna. It is not far away from the antenna. It is near to the antenna, therefore we call it near field. Then it is reactive because the field in this region is mostly predominantly or dominantly reactive in nature. Radiative in nature will be there, but the dominating factor is reactive, which means energy is mostly conserved in this nature, in this region. In this region, energy is mostly conserved in this region, which means energy is mostly stored in this region. So energy comes out of the antenna, then goes back to the antenna as if it is a capacitor or inductor. As you know, energy in the inductor and capacitor, energy is stored. So you can store energy in capacitor or inductor and take away energy from inductor or capacitor. These are called reactive elements. So similarly, this region, in this region, the energy is stored or taken away. So this is the energy storing region, that therefore it is reactive region. This is called the reactive near field. And this region is equal to lambda by 2 pi. So the radius of this blue region is equal to lambda by 2 pi, or which is approximately equal to 0.16 lambda. 1 by 2 pi is approximately equal to 0.16. So this is 0.16 lambda. Then beyond that, if you keep on moving, then up to radius is equal to 5 lambda, from radius is equal to lambda by 2 pi to radius is equal to 5 lambda. This region is called radiating near field. Again, it is radiating near field, but here the radiating fields dominate, not the reactive field. So energy conservation, so energy storage is not important in this region. Dominating part is radiating field. So field gets radiated from here, fields get radiated, but it is again a near field. Then beyond this, as you keep on moving away from this, so if it is R is greater than 5 lambda, then that field is called the radiating field or far field. So these are near fields. Then that region which is away from R is equal to 5 lambda is called the far field. So this is for small antenna. If we go to the other case, so we consider a volume within a radius or diameter of D, which is greater than 2.5 lambda. These are called large antennas. For example, if you look at the dish antennas on the towers, these are all large antennas. And the antennas in your mobile phone are called small antennas. So for large antennas, again we have same type of fields, reactive near field, radiating near field, and far field. Now if you look at the reactive near field, there R is equal to 0.62 into root over of D square by lambda. So that is from the antenna up to a radial distance of 0.62 root over of D square by lambda is called reactive near field for large antennas. Then beyond that, up to a distance of R is equal to 2D square by lambda is called radiating near field. And you can see the electric field distribution in the reactive near field and in the radiating near field. In the reactive near field, the distribution is erratic. It does not follow a particular pattern. But as you come to radiating near field, it starts forming a pattern, particular pattern. But again, there is some erraticness there. This is called the Fresnel zone. The radiating near field is also called the Fresnel zone. Then away from that, that is R greater than 2D square by lambda, away from that, the field is called the far field, or in the far field region, this is called Fraunhofer's field or the far field. There, the radiation pattern is well defined, and there is no loss as you keep moving around the field. So that is what it is for the field. Then next. So now consider the properties of reactive near field. In the reactive near field, the electric and magnetic field are in phase quadrature. That is, their phase difference is pi by 2, approximately pi by 2 as in case of reactive device. So electric field and magnetic field are in phase quadrature. Their wave impedance, you can observe the wave impedance is highly reactive in nature, eta. That we define wave impedance as eta. That is highly reactive in nature. The energy is evanescent, which means energy is not propagating. It is mostly stored. So this is the property of reactive near field. Now, radiating near field, in this case, E and H are mostly in phase. This is the difference between reactive near field and radiating near field. For reactive, it is pi by 2, phase difference is pi by 2. Therefore, it is stored. Now they are in phase. Therefore, it will not be stored. It will be radiated. So E and H are mostly in phase. The wavefront is non-spherical wavefront. For the waves, you don't get spherical wavefront. So the pattern varies with distance. Therefore, as you keep on changing the distance, the radiation pattern will vary. It will not remain constant with distance away from the radiating source. As you keep on moving away from the radiating source, the pattern will be different. Pattern is the distribution of electric field, the locus of distribution of the electric field in this zone. Then you come to the radiating far field. In the radiating far field, E and H are mostly in phase, because if they are in phase, then there will be radiation. If they are in phase quadrature, there will be storage. So they are in phase. Waves of spherical wavefront. Pattern remains uniform with distance. As you keep on changing the distance, they will not change. The pattern will remain same. Since the pattern will remain same and E and H are in phase, so we will have non-evanescent energy and the propagating energy, propagating power. Wave impedance will be real. If the wave impedance is imaginary, then there will be, because of the imaginary part, you will get the reactive portion. So the reactive portion is gone. The wave impedance will be real. In the radiating near field, the wave impedance is complex. In the reactive near field, wave impedance is highly reactive or mostly imaginary. Very small amount of real part here. It is purely real. The propagating power is predominantly real. So this is about the field regions. Then we will come to the parameters of the antenna. That will start after 5 minutes. Let us take a break of 5 minutes.